I'd like to start just by thanking Martin and INSAIT for the opportunity to visit Sofia, and it's my first time in Bulgaria. I've had a wonderful time so far. We'll see how the lecture goes, but thanks very much for the opportunity to address all of you tonight. So I was going to talk about a project that's been going on for a number of years and how to program the kinds of modern computer architectures that we see emerging for large-scale computation. And this is a project that started at Stanford with a few of my students and has since expanded. And now we have collaborators in the national labs, so Los Alamos and SLAC are national laboratories in the United States. And of course, NVIDIA is a computer architecture company. So the goal here is to think about how to program modern supercomputers. And this is a picture of the two most recent computers built by the US government. These are one and a half, roughly, exaflop machines. So that's an awful lot of computation. That means like, 1.5 billion or something like that operations per second. These machines take up most of a building. They have tens of thousands of high-performance processors in them. But they're also, interesting from the programming point of view. Probably the two most important things about them is they don't all have one kind of processor. So they're both CPUs and GPUs in these machines. And they have what we would consider to be a non-uniform memory, meaning that the memory is actually not just one physical memory, but is actually split up into lots of pieces, and there's many different kinds of memory, different sizes of memory, different speeds of memory throughout the machine. All right? And this creates issues for how you want to write software for such machines. Now, the thing is that, while these are the machines of, you can think of these machines as the machines of tomorrow. Like, it tends to be the case that, the high-end machines of today become more commodity-like machines within a decade or two. So we could expect that, our existing machines that we have access to as ordinary people every day will look more like this in the future than they do today. But in fact, even in this laptop, in this phone, it's already a highly heterogeneous distributed machine. So there's more than a dozen processors of different kinds in this phone, many different kinds of memory for each of those processors. So in fact, some of these problems I'm going to talk about exist already today on the kinds of machines we have available to all of us. All right. And so what exactly am I talking about? Well, so here's a little picture of what these machines look like, and you probably can't, maybe you can't see the screen or read it too well. But this is lots of different machines essentially tied together with a network. But then inside of each quote-unquote machine is a whole hierarchy of more machines. So there are CPUs and GPUs even inside, what is technically considered one single machine here, and then many, as I said, many different kinds of memory that are accessible. Some only to the one kind of processor. Some of the memories are only accessible to other kinds of processors. Some memories can be used by both. All right, and so programming these things and orchestrating all the computation and data, especially if you want to get maximum performance, is a non-trivial problem. All right. So the question I want to talk about is just how we should program these machines and how we should think about them. And the first, kind of like if you only remember one thing from the talk, it would be that data and not compute is actually what matters in programming these machines. Okay. And so now let me take a moment and just digress a little bit on the history of programming. So from the moment that people started programming real modern computers, say in the 1950s, there's been a real focus on the computational part. So like in our programming languages, if you're familiar with that, we have a lot of ways of talking about how you organize the computation. You can organize it into functions. If you're doing parallelism, you can organize it into threads. There's different kinds of synchronization primitives. There are different kinds of constructs within a function for expressing, different operations, okay? And all of this is very much about the control. We have much less developed ways of talking about the data, okay? And there's a fundamental way in which programming tends to hide the complexity of real machines. I mean, programming is always to some degree about making it less burdensome to make these machines do something useful. But historically, we've really hidden the structure of the memory completely from the programmer. So if I want to have a data structure like an array or just some collection of images or something like that, there's usually ways in the programming language to say, I want this thing, and it just lives out there somewhere in the memory. And we don't think about exactly where it is. But in machines like the ones I showed you in these pictures, I mean, speed of light matters a huge amount when you have warehouse-sized machines. And so time and space really matter a lot. And the kind of time-space allocation of the data is a first-class programming concern. In particular, it's even a concern just because your data doesn't even fit in one memory. Your data is going to be broken up into pieces and spread out across the machine. And how you express that at the programming level is not something that that we have really thought a lot about historically in programming languages. Okay, so this project, probably more than anything else, came to be about how do we think about talking about the organization of the data, the distribution of the data, computation over the data when it's inherently going to be distributed. And we have to talk about that at the program level. Like, we can't just hide that because that needs to be part of what the programmer is responsible for. All right. Okay, so the project is called Legion, and it's what's called a task-based programming system. So task-based programming is a kind of parallel programming approach where fundamentally these tasks are asynchronous operations. So tasks are just functions you want to perform, and it can be run in parallel. So I might have more than one task going on in different parts of the machine at the same time. And these tasks are intended to work on large amounts of data. So they generally work on some bulk arguments, not just a little bit of data, but a lot of data. So a task will be something that takes a very large array or some other kind of collection as an argument. And task models are actually very popular today. They've become very popular in the last half dozen years. So you see them used a lot in cloud computations and in large-scale machine learning. So systems like Spark, Dask, TensorFlow, PyTorch, you may have heard of some of these. These are all task-based models, okay? And then in high-performance computing, this is the field in which, the context in which I was, me and my collaborators have been doing this work. There's a bunch of, kind of research systems, and now increasingly used in practice for high-performance computing, for scientific computing, large-scale simulation, things like that. All right. So a little bit more about tasking and the programming model. So I said these tasks are just functions that are supposed to work on a lot of data, and we can think at some level these tasks are just one way or another. The program gets a hold of these tasks. I'll talk a little bit more about how that works in Legion at some point. And you have some dependencies between the tasks, and the edges here between the tasks just represent ordering constraints. So for example, task 1 and task 2 up there, they have no edge between them, so they can run in parallel. They can be scheduled at the same time. But task 1 has to finish before task 3 can run. Okay, so there's some directed acyclic graph of dependencies like that that tells you, partial order on the execution of the tasks. And then you have data collections, and here I've tried to indicate that each task takes one argument. The arguments are laid out in the same kind of orientation as the tasks. I separated them here to make the picture not too ugly. But task T1 is going to take A1 as an argument, task T2 is going to take A2 as an argument, and these are large collections. These are some kind of significant amounts of data. And then we have a machine. All right, and this machine might have some CPUs, like an x86 processor. It might have some GPUs that run CUDA. And then there's these different kinds of memories over here. So frame buffer, NUMA domains for the CPUs. Doesn't really matter what the names are, but there's a bunch of different memories, some of which are usable by the GPUs and some of which are usable by the CPUs. And then to run one of these programs on this machine means you need to have an assignment of these tasks to these processors. You need to say which tasks are going to run on the CPUs and the GPUs. And then you need to have a compatible assignment of the data, meaning that if some task is going to take an argument, that data needs to be placed in that argument needs to be placed in a memory where the processor on which that task runs can actually get at it. Okay? So there's a fairly involved mapping of these programs down into the machines. All right? But you don't really want to deal with this as a programmer when you're writing your program. Okay? You'd like a little bit more abstract level where you don't have to worry about a specific machine. Okay, so for the most part, I'm just going to talk about tasks and arguments and not talk about the details of the underlying machine. But just bear in mind that these programs with these different collections and different tasks, they have to be embedded, ultimately mapped, as we say, onto these machines in some way that makes sense for the execution of that program. All right, so now I'm going to talk about data in Legion. And I'm going to talk about how we think about partitioning data for these distributed machines. And then I'll say a little, and I'll talk about that just first just in the abstract about what it means to partition data and what the model is. And then I'll talk about the actual piece of Legion that does partitioning and what the primitive operations are. And then I'm going to conclude the talk. This is basically, that's the whole talk. It's going to be about how we kind of go beyond what people have done before in programming the orchestration of data. And then I'm going to give some examples at the end drawn from a wide range of applications. Okay, so the reason for focusing on partitioning, there's a lot of other things in these distributed programming models that are interesting. But the thing that's really distinctive is that the data is distributed. So the data has to be partitioned across the machine in order for you to do anything useful. All right, so and so the question is, how should we talk about that? And if you look at what I would call the traditional distributed programming systems, the partitioning mechanisms are very primitive. All right, so you really can't say very much, and it's particularly hard to build software that composes well. All right, and so I'll say a little bit more about that later. But let me just take it as a starting point that this is not a very well developed topic. Okay, so to motivate our approach to this, let me just start by talking about how you might partition a graph. So we have some graph of nodes and edges, and let's just say that we're running on a relatively small machine, and so we just want to partition it into 3 pieces, and then we'll be able to work on the 3 pieces in parallel. Okay, so we just want to be able to say, take this graph and we want to cut it up into these 3 pieces. So how would we program something like that? Okay, so let me start by saying, okay, first of all, let's just focus on the nodes. All right, so we're not going to look at the nodes here are the circles, all right? And then separately there are the edges, which are the lines between the circles. So I'm not going to talk about the edges at all. I'm going to simplify the problem even more and just say, I just want to chop up these circles into these 3 sets. And I want some way to talk about that that I can program. So how would I go about doing that? Well, I start with a big collection of just all the nodes, okay? And now, for this particular application, I haven't said yet what it is. This is an application, this actually comes from an electrical circuit simulation. And so when you're simulating the electrical circuit, the wires represent, so the edges represent wires, so electricity flows along those along those edges to the circles, and then it just goes around the graph according to the rules of standard electrical engineering kinds of principles. And so what's going to happen is that these pieces are going to have to talk to each other. Even though we might, say, take the upper left-hand piece and have it running on some processor somewhere, at some point, some information is going to have to be exchanged with another piece when it crosses across the boundary. When electricity flows across the boundary in the simulation, then we have to talk to the other piece and tell it that what's happening, okay, on our side. So the first thing we need to do is we need to split these nodes into what we call the private and the shared nodes. And this is a very standard thing in lots of simulations. So essentially the private nodes, if you look at the private nodes colored in blue, they're in the interior of a piece. They are not connected to a circle in any other piece. All right, so these are the nodes that don't need to communicate outside of their piece. Whatever happens on those nodes is going to stay within the piece because all the edges, all the wires that come out of those nodes are still within the piece. And then the red nodes are the shared nodes. These are the ones that are on the boundary of a piece. They have an edge that connects to another red node in a different piece. Okay, and so information during the simulation is going to have to be exchanged across that boundary, and that means, you know, some kind of communication is going to happen there. All right? So the first thing we need to do is kind of, you know, be able to distinguish these private nodes from these shared nodes, because we're going to treat them differently usually in how we, in our program. Okay? So then we can split each of these private sets. You know, we had the big set of private nodes, all the private nodes for all the pieces. So now we can just split that into the 3 subsets, you know, for the 3 pieces of the graph. And so here, P1 is just the private nodes of this piece in the upper left-hand corner. You know, and S1 is the shared nodes of that piece. And so now, you know, for each piece, we have a set of private nodes and we have a set of shared nodes, and we're getting close to the organization we need to run the simulation. All right, but there is one more thing we need, okay? And I said, you know, they're going to have to communicate with things outside of the piece. Like these red nodes in piece 1 have to talk to nodes in, you know, to have to communicate over edges that are connected to nodes in other pieces. And we'd like to be able to name that set as well for the purposes of writing our program, okay? So that means that these shared nodes, we're also going to have another way of looking at them, which is going to be what we call the ghost nodes. All right, so the ghost nodes of a piece are the nodes that are connected to that piece but outside of the piece, okay? So here you can see for piece 1 has some private nodes that are in the interior of the piece. It has some shared nodes that are on the boundary of the piece. And then it has these green nodes that are one step away from the boundary outside the piece, okay? And every phase, every task is generally going to have to work on all 3 of those sets for every piece. It's going to need to know what are the private nodes, what are the shared nodes, what are the ghost nodes. And the interesting thing about this is that these shared nodes, you know, if you look at the red subsets, S1 through S3, that is just a different view of the shared nodes from G1 to G3. So the ghost nodes are just a different partitioning of the shared nodes. All right, so the ghost nodes, you know, you'll have 3 subsets of nodes, you know, 1 for each piece. Together that represents all the shared nodes and also the red subsets, the S1 through S3, you know, that's a different view, okay? And so this is one of the first lessons, I think, about partitioning data for distributed execution, is that you often need multiple partitions of the same data. You need multiple views of the same data and different ways of different subsets of the data for different purposes, okay? And this is something that you generally can't express in previous approaches. So here I've introduced this data structure over here on the left. You know, we have sets. Every box in that picture represents a set of nodes, okay? The hierarchy indicates subset relationships. So if a node is below another node, that means it's a subset of the one above it. And then the horizontal bars represent partitions. And so you see the shared node has 2 different partitionings of the data, okay? All right. So then tasks would be written looking like this. So you might have a task that's going to distribute charges, and it will take in private, shared, and ghost nodes for a particular piece. These things are called regions in Legion. Okay, that's just a name for the kind of collections we have. And then down here we see, you know, there are some declarations of what you're going to do with those things. So, you know, you're going to read from some fields of the wires. That's the first thing. So RW is the region of wires. And then you're going to do reductions to the private nodes, the shared nodes, and the ghost nodes, just to the charge fields of each one. All right? So this is what the tasks look like. So you would name which sets you're going to work on. And just notice that, you know, that here, you know, I forgot to say, tasks are the unit of parallel execution. So these are the things that, you know, the computations that will be distributed around the machine. Regions are these n-dimensional tables or tensors, okay, and they have typed fields, so you might have multiple fields in a region. And then these privileges declare how the task is going to use the regions. And the point I was jumping ahead is that, you know, this task in particular uses both views of the shared nodes at the same time. So it's accessing some shared nodes, it's also accessing some ghost nodes, okay? All right. Okay, so now the observation then is that, you know, this problem of needing to have multiple ways of viewing the same data, okay, so multiple different ways of dividing up the same data is very common. And so you're really going to need this if you want to have scalable software composition. And so here's, I think, you know, one of the, you know, kind of the strongest argument one can make for this. So let's say that you have two libraries written by different people that are intended for parallel distributed execution. So somebody writes library 1, somebody else writes library 2. You know, what are the chances that they wanted to look at the data in the same way? Okay, pretty low, especially if they didn't talk in advance. I mean, like, you'd like people to be able to write libraries independently and then use them in your own code, all right? And so then the question is, how can you compose them? Well, you know, if you don't allow for multiple different partitions of the same data, you will have a very hard time composing them, right? Because the chances, you know, programmer A will pick one strategy for partitioning the data, programmer B will pick a different one, and if you're only allowed one view of the data, then you won't be able to put these together. So if you want to be able to compose parallel distributed libraries, then you need to be able to allow for different views onto the data, okay? And the database people know this. I mean, in databases, the notion of a view, that term comes from databases, and the idea that you might have different ways of, you know, looking at the data is a standard idea in that world, okay? It has not been adopted in the parallel programming world so much. And so here are just some examples of where you might have multiple libraries. You might have a simulation that somebody wrote. That simulation might use a solver, like a linear solver, as a subroutine. And you might have a visualization library that makes pretty pictures, you know, of the simulation at the end. And all of these are written as libraries that work, you know, in distributed fashion. They're all going to have different needs for how they view the data, and you're going to want to be able to put them together, okay? And today, the way this is done is very, very inefficient. Okay, essentially the way these things get composed today is because they don't allow for multiple views of the data. You run one thing, like your simulation, for a while, and then you have to stop and copy all the data into the format that the solver wants. Okay, and then you restart everything, let the solver do its thing. When the solver's done, you stop, copy everything back to the way the simulation wants it done, and you spend all your time moving the data around instead of actually doing any compute. And this is why I said at the beginning that data is what really matters, because this communication is tremendously expensive, all right? So this will be 90% of the energy, 90% of the time, you know, if you try to build out of building blocks like this. And this is why so many of these applications today, I think, are written in a very bespoke way, where they're very much hand-tuned over years and years to make all the pieces fit together very tightly and in a customized fashion to eliminate those inefficiencies. But what you would really like is be able to, you know, if you're going to have a productive ecosystem, you need to be able to write libraries, you need to be able to compose them. And so I think this is a different way of looking at it that I hope will have, you know, advantages for developing this kind of software in the future. All right. Okay, so now, I didn't explain exactly how you do this partitioning. All right, so now I want to talk a little bit about the sublanguage, the piece of Legion where you actually do partitioning and how that works, okay? So it's really a little language, okay, very small language actually. There's dozens of operations, but only really a couple of different kinds of operations, okay? So I'll talk about those now. Each of these primitives is designed to be something that you can implement efficiently on a parallel distributed machine. And then also their composition, you know, you can basically write little programs, partitioning programs in these things, and express very complex partitioning strategies. So let's talk a little bit about that. So let's come back and say, okay, like, how would we have done this programmatically in Legion, all right? So let's just focus on, okay, first thing we wanted to do was to identify the blue nodes and the red nodes. Okay, and Legion has no idea how you want to Legion is just a runtime system. It implements whatever you tell it to do. It's not magic. It doesn't know that this is a good partitioning strategy for this graph, all right? So somebody has to tell it that it wants, you know, these nodes to be red and these other nodes to be blue, okay? So here's a table or a tensor or a region, okay? And what we're going to do is just have an extra field, an extra column in this table that tells us whether each node should be shared or private, okay? And this is something that the program computes. So Legion is not like an automatic partitioner in the sense that it doesn't decide how to partition the graph. What it provides is primitives for the program to tell the runtime system how things should be partitioned. All All right, and then what's going to happen is the runtime system is going to take advantage of that information. Once you tell the runtime system what the important subsets of your data are, then the runtime system is going to manage those subsets for you. When they need to be copied, it'll do the copying automatically. When you say you want to change the layout, it'll change the layout automatically. So it understands what subsets you care about, but the program has to figure out the subsets. So it isn't about solving some graph partitioning problem. It's about giving you the primitives to describe, given you implement the graph partitioning yourself, and then you can describe to the system which subsets of the data are interesting for your application, right? So in this case, you would write some code to decide that this is how you wanted to break up the nodes, and you would put a bit in the columns there, in the SRP column, saying whether for each node it should be shared or private. And then you just say, partition this tensor by field. So use this field. All the things with the same value in the SRP column go in one subset, together. So all the things that are marked shared, will go in the shared subset. Everything that's marked private will go in the private subset. And then you've done the first level of the split I showed you, where you've named the private nodes and the shared nodes. And then you would repeat this for the other subsets that you wanted to name. Okay. All right, so these are what we call independent partitions. These are partitions that just kind of come out of nowhere. I mean, like the program has to say what the partition is explicitly, and then the system will do that. These are independent partitions that don't depend on other partitions. So like partitioning, there's another operation called partition into equal pieces. So you say, I wanted to split this collection into 5 equal pieces. That's another thing you can do. All right, you don't care what those are. Just give me any 5, any roughly balanced 5 subsets of this tensor. All right. Now the thing I want to talk about next is the dependent partitioning out primitives, because this is the composition mechanism. So allowing the system to compute new partitions from existing partitions. Okay, and this allows you to do things like co-partition, 2 sets of 2 data sets, in some intelligent way. So for example, in our graph example, if I pick some partition of the nodes, then I'd like to partition the edges in a compatible way. I'd like, edges that are attached to nodes to be in the same set of nodes to be in the same region, for example. All right, so this is for co-partitioning and for computing partitions from existing partitions. So there's only 2 operations in this category, and they have nice interpretations. So let's say we have 2 regions. Okay, and we've already partitioned region 1. And so region 1, I'm showing by color what the partitioning is. So there's a red subset, a blue subset, and a green subset. Okay, and that's already been computed. And now this region 1 has a pointer field into region 2. So there's references from region 1 into region 2, some association between the 2 regions. And so what partition by image means was we're going to treat region 1 as a function from elements of region 1 to region 2. And so this pointer field will just kind of inherit the color of the element, and then we're going to color the elements of region 2 as the same color as their source. And that defines a partitioning of the second region. All right. Now, interestingly, pointers don't necessarily give you injective functions. As you can see there are some elements in region 2 that have pointers from more than one element of region 1. Like the second element from the top has 2 pointers into it. And so those just get both colors. They're in both subsets. And so one thing I should clarify is that when I say things, we're partitioning the data, we're abusing the mathematical term partition. These aren't actually mathematical partitions. These are just naming subsets of the data. All right, and so these partitions these subsets that we name may overlap in cases like this. Okay, all right. And then partitioning by pre-image is just the inverse operation. So we've already partitioned the second region, in this case into 3 colors, red, green, and blue. And the first region has pointers into the second region. So now we're just going to color things backwards. We're going to follow the edges backwards to region 1, and then color each of the elements of region 1 with the same color as the edge. And the pre-images actually have an interesting property, which is that if region 2 is a disjoint partition, meaning the subsets don't overlap, then region 1 will also be a disjoint partition. Okay, very useful algebraic property of pre-images. All right. Okay, so now that's it. Okay, so with some independent partitioning operations and images and pre-images, which allow you to relate one partition, to compute a new partition from an existing partition, we can basically do everything we want to do. At least so far, we haven't found anything we can't express this way that we would like to express. So now let me tell you about some applications. Okay, so let me start with sparse matrix representations. So what's a sparse matrix? Well, it's just a tensor or table that doesn't have very many elements filled in. So most of the elements are zeros, and if you have if 99% of the elements of your matrix are zeros, you probably don't want to store all those zeros. You'd like some more compressed representation. All right. So here's a sparse matrix, not extremely sparse one, but one that's useful, for a slide. And there's a couple standard ways of partitioning sparse matrices. One is by row. So we're just going to have every element of every row be in its own subcollection. All right, so here I've just given each row a different color, the elements that are non-zero in those rows. But another one that we might like is to have a balanced number of elements, in each of these subregions. So here we've just split the elements so that there's 2 elements in each subregion, so that the work of computing over those in parallel over those subregions is going to be about equal. All right. These are 2 different representations, very standard and used in lots of applications. Okay, so how do you talk about this? Well, so let me introduce one kind of straightforward way of saying how this works. So let's say this is the notion of a coordinate tree. And all this is representing the entries of the matrix that are non-zero, as a tree structure. So here we have the first row there is the index of the row of numbers across the top is the what is it? I'm getting confused here. It is the index of the row on the left. Okay, so those are the row indices. And then the second row is the indices of the columns that have non-zero elements in them. And so, for example, if I look at the E element there that's colored in blue, that is in the 1, 3 position. Okay, and so if I go to the first row, okay, the element 1, and then I look at the third element, I get to E at the bottom. All right. So this is a standard way of kind of a systematic way of representing a sparse matrix. And then in actual implementations, you see these 3 arrays all the time. All right, so I won't go into the details if you haven't seen sparse matrices before. But if you look at sparse matrix representations, they basically have these 3 arrays. You'll have some kind of some kind of representation of what the rows are, what each element of the row that is inhabited is in a second data structure, and then a third data structure with the actual values. Okay, and this is actually very close to a standard sparse matrix representation. All right, now let's just call each of those 3 things a region, to make it a legion thing. All right, and now let's think about expressing the partitioning. So if I decide I want to partition the rows, I could start by saying, okay, just partition the rows, put every element in its own subregion. And now just use images to follow the pointers and paint the things that you reach the same color, okay? So the elements that each of those rows are attached to will be in one subregion, and then in the next data structure, the elements themselves, the actual values, will be in a similar subregion. So this is a way with an independent partition of the rows and then a couple of images to capture that particular sparse matrix representation, right? If I want to do the other one, well, I would start with the middle row, okay, the elements, and I would partition them equally, and then I would do images and pre-images to, color both the rows and then the elements. Okay. All right. So following some pointers backwards, some following some pointers forwards. All right. Okay. And so this is just to convince you that with those partitioning primitives, I can recover programmatically how to express standard sparse matrix computations. All right. Okay. Or I can, not computations, but standard sparse matrix representations and partitionings. All right, now, as I said before, the runtime system doesn't know how to do this partitioning for you. You have to decide what the subsets are, and you can use independent partitions and pre-images and images to compute these partitions. But once you've told the system that these are the subsets of data you care about, this opens up new possibilities for how you would implement things. So now, many of you will be familiar with NumPy, or some of you, I should say, will be familiar with NumPy, which is a very standard way of writing distributed code today. One way to understand the difference with Legion and something like NumPy is that in NumPy, the NumPy system has no idea what data you're moving, okay? It's just a bunch of bits. You say, I want to move these bits from here to there, and NumPy does that. It doesn't know whether those bits already exist somewhere else. It doesn't know whether that those bits overlap with some other set of bits. It's completely up to the programmer to orchestrate the movement of the data. If I tell you at this level instead, oh, here are the subsets I care about, and I'm just going to tell you for each task what subsets I'm using, and then it's up to the runtime system to figure out how to move the data to orchestrate that movement in the most efficient way possible. Now I can do lots of things I couldn't do when the runtime system had no idea what those bits represented, okay? So in particular, we can avoid extra copies, right? So we can write libraries now that will use the data where the client provides it and where the subsequent downstream operations would like to receive it, rather than having to first, by hand, essentially, move all the data into a format that the library expects, and then afterwards move it again into a format that the subsequent stage expects, all right? And so I can choose placement and layout now that reuses as much of what already has been done as possible, all right? And so we implemented this in a couple of libraries called Distal and SPDistal. These are actually little DSLs that generate libraries, little domain-specific languages. But let me give you just a flavor of what these things do. So you provide distal and sparse distal. So distal is for dense tensor algebra, and SPDistal is for sparse tensor algebra. You basically write down the tensor algebra expression you would like to implement. So in this case, this is matrix multiply. Okay, so you just say, I'd like a distributed matrix multiply library, please. Okay, and so then what Distal will do is generate Legion code that implements this, and it will use the partitioning operators and to express the some other additional information you give. So here are the actual specifications of the standard matrix multiply algorithms from the literature, and I apologize that this is probably a little hard to read. But basically what you're providing here is you describe the machine you're going to run on. Okay, you just, a lot of these algorithms are written for, say, an n-dimensional machine where it might be 2 dimensions, 3 dimensions, and some of the algorithms are actually 2.5 dimensions. Okay, so you have to say a little bit about what the abstract machine looks like. You have to describe the data partitioning, all right? So that's the middle column here, and these are the actual specifications. So just a handful, just in this case, just one specification for each matrix. And then you have some scheduling operations that say something about how the tasks, the kernels that work on the data should actually interact with the distribution of the data. So like what order the loops should be in and things like that, okay? And these schedules are all less than 10 lines of code. All right, and then what you get out is an implementation of each of those classical matrix multiply algorithms. All right, and so here are some performance numbers. And so so Cosma is the latest and greatest distributed matrix multiply algorithm from a group at ETH, and our implementation gets to 95% of that. And then Scalapack is the standard library that everybody uses in practice. It's the industrial strength one, and we're about 25% faster than Scalapack in these kinds of standard benchmarks. And so that's a CPU story, and then there's a similar story on GPUs. Okay, and so you can see the Cosma performance here in the yellow line, and this is actually our Cannon's algorithm on the blue line. And this sawtooth behavior is actually a property of Cannon's algorithm. So you get that. That's just the way the Cannon's algorithm works for different machine sizes. It doesn't have a nice flat performance profile, and that's what Cosma fixes. So Cosma actually levels out that performance a bit. But then the advantage is that this generalizes to all of tensor algebra. So now if you have some other tensor algebra expression that you would like to implement, now you can do that. And these are not ones necessarily that people have spent a lot of time hand tuning and writing libraries for. Okay, and the gaps are much, much larger for things that are less commonly used than matrix multiply. Okay, so those are CPU numbers and some GPU numbers. All right. And then I also mentioned before, this also works for sparse tensor algebra. So here are some performance plots of the Legion version of sparse tensor algebra versus two standard libraries called Trilinus and PETSI that do sparse tensor algebra. So in the upper left-hand corner is SPMV, which is a standard operation that people do all the time when using sparse matrix vector multiply. It's used extremely commonly in everything from scientific computing to machine learning. And you can see that Legion's a little bit better than Trilinus and PETSI, and these plots have error bars around them because these are sparse matrices, and different matrices have different sparsity patterns, and so the performance varies depending on what the input matrix is. Okay, and so it's not just the same. When in a dense setting, it doesn't matter what the data is, the performance will always be exactly the same. In a sparse setting, depending on how many zeros you have, you will get different performance. Okay, and so you can see that Legion's doing a little bit better than these other libraries. But then if you move over to something that is not, again, a standard sparse computation that has where people have written lots of hand-tuned libraries for it, then the gaps are much larger. And you get much better performance. All right, so another important application area is deep neural networks. So FlexFlow is a Legion library for deep neural network training and inference. And the basic idea behind FlexFlow is, why would we do a new library for deep learning? Okay, well, it turns out that the standard libraries PyTorch and TensorFlow have very limited ability to partition the data. They basically understand one or two ways of partitioning the data, and they don't try anything else. And there's a lot of other dimensions in which you could partition the data that may or may not turn out to be a good idea. Okay? And so the first observation was, well, we could just try this and see if we can come up with strategies that have better performance, exploiting the ability to partition data in novel ways. But the second idea was, well, we could also automate this partitioning process, because once you have a language for expressing how to partition the data, you can just write a loop that searches over different partitioning strategies. Just try lots and lots of partitioning strategies and see if any of them are any good. So you don't have to come up with a partitioning strategy yourself. You could have some search procedure that will discover the partitioning strategy for you. And you could do that for every layer of the network. So every layer of the network could have its own partitioning strategy. That may or may not be better, all right? But then you'll just pick the best one at the end. Okay, so here's a kind of a pictorial representation of this on 4 GPUs for a standard network. I think this is the INSAIT network. And so here we just have done the standard data parallelism. So the sample dimension is the data parallelism dimension. And this is the standard thing that TensorFlow and PyTorch do, all the systems do it. And then here we're just comparing it against one other dimension, the parameter dimension, so how you spread the parameters out, divide up and spread out the parameters of the network. And the reason for that is it's easy to show two-dimensional plots on a screen. We could have had more dimensions, but this one just made it easy to show the effect. So in TensorFlow and PyTorch, you would get the same partitioning strategy for every layer and only in the sample dimension. But if you run FlexFlow on this and let it search, it's going to pick interesting partitioning strategies for some of these layers. There's a lot of data parallelism in here, but then you'll see parameter parallelism as well, and for some layers it does both. It partitions in both the parameter and the sample dimensions. Okay? So you get very, very complex partitioning strategies out of FlexFlow. And does this make any difference in practice? Well, so here is a comparison of FlexFlow against Megatron. And Unity is the latest version of FlexFlow. So this is comparing the old FlexFlow against Unity. And so Megatron is this handwritten implementation from NVIDIA that incorporates every known optimization. And you can see that FlexFlow is getting very close to what Megatron can do. But then this applies, of course, to all the other networks as well. And so you apply it on other networks, especially ones that people haven't worked on as much. You do see big speed ups over other approaches. Okay. All right. So last thing I want to tell you about is a small advertisement, which I won't go into any detail. But if you're not somebody who's into supercomputing and you don't really care about all this partitioning stuff, sounds like a lot of work. But you like to write NumPy, well then NVIDIA has adopted Legion as the substrate for a reimplementation of NumPy that does all the partitioning automatically. So this is a drop-in replacement for NumPy called QNumeric that will take your NumPy program and run it parallel and distributed out of the box, okay, with no additional effort. And so it has its own heuristics for how to partition the data. Basically, it takes the NumPy arrays and splits them up, and it knows about the different operators and what good strategies are for different operators. And the key idea here is again, to leverage the partitioning language in Legion to do something intelligent and automated for the programmer. And this very much relies on having multiple views of the data that I talked about at the beginning. And also relies very heavily on the dependent partitioning operations, okay? So this is now an NVIDIA product. It's in beta. It's open source. Anybody can get it and try it out. All right, and this just became a beta last month, so this is all relatively new. Here's a kind of an example. So a solver for a fluid flow, written in 200 lines of Python, fairly sophisticated solver. And this is unmodified code, and it runs out to 2,000 GPUs. If you run it with QNumeric. Okay. And then just one more bit of information. So Legate sparse is another Python library for providing this kind of the sparse methods and data structures. And Legate sparse is also is going to this model of trying to replace Python libraries that work on bulk data structures with accelerated versions is something that we're picking up as a kind of a theme. So this is a drop-in replacement for the sparse part of SciPy. And we used SPDistal to generate the kernels for this, but then used some of the QNumeric technology to automate the Python pieces. And so here, this is a conjugate gradient solver in Legate sparse solving a 2D Poisson problem. Main thing here is that this is just the standard thing you would write in SciPy, and then you can take it and you can run it out to hundreds of GPUs on a big system and solve a really, really large problem without having to do any parallel distributed programming yourself. Okay. Similar story here for a geometric multigrid solver. These are normally things that are really tricky to write because they have fairly complicated partitioning, but in this case, it's 300 lines of Python to do this, and you get good performance. All right, so to summarize, in distributed computing, data partitioning is key. I mean, this is the thing that makes it different from other kinds of programming. And Legion has this expressive data partitioning system. I think it's really the first effort to really kind of systematically understand, what programming data partitioning should look like. The approach we took was to have these independent partitioning operators and then a few dependent partitioning operators based on images and pre-images to allow you to program complex partitioning strategies. And what this has enabled for us is the ability to write flexible libraries that can adapt to clients, like the tensor algebra work I told you about, and also to automate partitioning in higher level tools, things like FlexFlow and QNumeric. And with that, I'm going to stop. Thank you very much for your attention.